Okay, welcome back. We're going to continue working on linear algebra with Python and Numpy. And in this particular case, we're going to be looking at some special matrices. I'll show you about eigenvalues and eigenvectors, and then we'll look at a few other matrix operations that we can do. So if you want to build an identity matrix, I'll just call it I is equal to, now you can probably guess NP dot, and if I just start typing, identity is one of them. It tells me it's going to want just an n to come in. So if I do identity and open a parentheses, this will return the identity array. It's square, so if I do a 4 here, that will print for me the 4 by 4 identity matrix. Right? If I did a 10, there's the 10 by 10 identity matrix. So really easy to build a quick identity matrix. Okay, the zeros matrix, I'll call it Z, np.zeros of. Now zeros wants a shape, right? Because we could do a zeros vector as a row, a zeros vector as a column, or a zeros matrix. So I'm going to give it a shape that comes in as a tuple. So if I did like a 5 by 5, printed that guy, it gives me a 5 by 5 matrix of zeros. If I did 5 by 1, it gives me a 5 by 1. If I did 1 by 5, it gives me a 1 by 5. Now this is really handy for pre-allocating memory. So if you're building up some solution in a loop and you're going to fill in all these entries later, it's handy to build in or to build everything in terms of zeros first. A ones matrix you can build in kind of the same way. You can probably guess what it's going to look like. So I'll say, let's see, ones is equal to np.ones. And it wants a shape also, so if I did like a 3 by 5 of ones, it'll give me that matrix. Again, this is good for pre-allocating memory. The ones I would use to pre-allocate if I know that I've got at least 1 in everything, and then I'm going to fill something in if it's not 1. Or maybe I'm going to multiply it by something every time, whatever. Okay, so those are 3 handy little special matrices that you can build. There's lots of others. Eigenvalues and eigenvectors. So if you don't know about eigenstructure of matrices, that's coming in your linear algebra class. But for right now, I'm going to presume that you know about them. And they're going to come from the linalg package. So np.linalg.eig. There's lots of ways to do it, but .eig of a matrix. And I've got the matrix A still stored in memory. So if you bear with me, scroll way to the top. There's my matrix A from a previous video. Scroll back to the bottom here. Now, it actually gives me 2 things out, right? So if I print this, it gives me an array of the eigenvalues, and then it gives me a matrix where the columns are the eigenvectors. So if I unpack that, I can unpack it with the commas, vals vex equals those guys, and then I could say vals, or let's print the vals. There's my eigenvalues. And then I could print the eigenvectors. Right, now the eigenvectors are the columns. So if you wanted to pull them out one at a time, I could say V1 is vex of colon comma 0. Suppose I should be consistent. V0 is. Right, and it pulled out that first one. I could even normalize that and say, well, let's see, it should be a unit vector. I could normalize it so that the top entry is a 1. So I could say divided by vex of 0, comma 0. That way the top entry is a 1, because remember an eigenvector is unique up to scaling, so you can scale it kind of however you want. You could normalize it by the sum. So now the sum is 1, and you can interpret these as probabilities. A nice handy little tool when you're working with Markov chains and probability vectors. Right? Similarly, I could do V1 is vex of colon comma 1. V2 is vex of colon comma 2. And of course, we can check that these are eigenvectors. If I just did A times V0, I should end up with 12 times what was in, because here's this, I should end up with 12 times what was in geez, sorry, I just lost my train of thought there. You should end up with 12 times this eigenvector, which is exactly what we got. Whew, okay, I'm back. Sorry about that. I'll leave it to you to actually verify that. Right? Same thing for this, right? About negative 0.4 times this should give me these guys. And here, negative 5.7 of this column should give me this. Okay, so pulling out eigenvalues and eigenvectors is relatively easy. A note of caution for those of you that are coming from MATLAB, I believe the order vals vex is backwards from what MATLAB does. I think it's vex vals for them. So be careful with your naming convention. Okay, and the very last one, trace of a matrix, rank of a matrix, and the condition number. So if I have my matrix A and I do A dot, okay, trace is one of those natural functions for a matrix. So if I do A dot trace, the trace of the matrix A is 6. And we can verify that by saying 1 plus 5 plus 0 is 6. The trace is the sum of the main diagonal. Okay, the rank, this one comes from LinAlg again, so I believe it's matrix rank. There it is, matrix underscore rank of A. Remember, rank is the number of linearly independent rows or columns, and it's 3. If I do B, this is a singular matrix. I should get something less than 3 because it's a 3 by 3 matrix, it was singular. So rank is relatively easy. And then the condition number, np.linalg.conditionNumber.cond of your matrix, right? So this measures the relative size of largest eigenvalue to smallest eigenvalue. And if it's a non-square matrix, it's largest singular value to smallest singular value. If you don't know about condition numbers, that's coming sometime later. So this is some of the special things that you can do with linear algebra and matrices in Python. And we're going to call this video good.